Kirchhoff and Bunsen in the middle of 19th century studied about different colors exhibited by the atoms when burnt on a Bunsen flame. Certain atomic samples are heated, light of characteristic color is observed. You might have seen in the inorganic chemistry laboratory for identification of the atomic sample by simple flame test. This is due to the emission of visible radiation at wavelengths characteristic of the elements in the sample. So when certain atoms are burnt, so usually the color of the flame is used to change it. It's due to the atomic emission of energy in the form of visible light. Compounds containing lithium, sodium, potassium, calcium, barium ions can be recognized by their characteristic colors emitted after receiving thermal energy. Lithium gives red color flame, sodium yellow, potassium lilac, some kind of magenta or light purple color. Calcium ions gives you brick red color, whereas barium when burnt on a flame it gives green color. Bohr atomic model strongly suggests the occurrence of atomic spectra. The electrons of the gaseous atoms are in orbitals with specific energy levels that are characteristic of the element. The electrons in the outer orbitals of the atoms may absorb thermal energy, therefore promoted to one or more higher energy states. So absorption of energy is quantized, that is specific, which corresponds to the difference between the energy levels which are also quantized, that is specific. This process is called excitation. Excitation is nothing but the absorption of energy. So that energy matches to the difference between the higher, lower and or upper and lower energy states. So therefore absorption happens. So what happened? The time spent in the excited state by the electrons in the atom is short-lived, very short. So deactivation occurs from the thermally excited atoms to the original lower energy states very rapidly, which promotes the photons to be emitted. Or the deactivation of the thermally excited atoms happen via liberation of the energy in the form of light. The light photons have energy that is exactly equal to the difference between the upper and lower energy states by the relation delta E equals to E upper minus E lower. We know that energy is always proportional to frequency, and arranging the terms, that energy difference is also equals to the energy corresponds to the frequency, and the frequency can be written as C by lambda. Therefore delta E equals to Hc by lambda, where H is a Planck's constant, 4.132 into 10 power minus 15. So speed of light is 3 into 10 power 8 meter per second. So when we submit all those values h into c, we got the variable numerical 1240 by lambda, that is nanometers, and rearranging the lambda and delta E, we obviously get the lambda value as 589 nanometers. As the atomic energy or characteristic of the element, the energies and wavelength of light emitted also characteristic of the element. So absorbed energy is characteristic for that particular element. Therefore, emitted energy is also characteristic. So the atomic emission spectrum of sodium consists of approximately 20 lines. In that, the most intense is at 589 nanometers. So that 589.3 nanometer can be obtained by substituting the potential energy values when excitations happens from 3s to 3p. The potential energy difference from upper minus lower is about 2.1. Therefore 1240 divided by 2.1 gives you the wavelength that corresponds to the energy difference between 3s and 3p. So the wavelength corresponds to the energy difference 3s to 3p is 589 nanometer. So therefore the most of the population of sodium atoms undergo this kind of electronic transition, since it is very easy for them. So that 3s to 3p electronic transition is most favorable. Therefore when atoms excited from 3s to 3p, at that stage they are short-lived. Therefore the deactivation occur through liberation of this energy in the form of visible light. So the light wavelength would be 589.3 nanometer. And similarly, when the 3s1 electron jumps from 4p to 3s1, it emits the light of 330.2 nanometer wavelength. Similarly, from 3d to 3p deactivation liberates the light of 819 nanometer. Among the three discussed here, 589.3 is the D line of sodium, which is much intense because most of the majority of the population exhibit this type of the electronic transitions. So therefore less intense lines at 330.2 and 819 nanometer are due to 4p to 3s and 3d to 3p respectively. So in this way, the atomic absorption lines and atomic emission lines are characteristic for that particular atom, and both are complementary. That is absorption wavelength, whatever the absorbed energy is there for the particular atom, exactly the same energy is emitted as such, since no external energy loss process may be there in the case of atoms. So therefore absorption lines and emission lines are same for the atoms. So therefore flame emission spectrophotometry or flame photometry is one of the technique where the spectrometer measures the intensity of the emitted light from the thermally excited atoms. So in the case of flame photometry, so the atomic sample need to be vaporized and getting excited. After exciting, they use it to emit the light in the form of emit the energy in the form of light. So the light photons intensity emitted is measured using a spectrometric detector. So the intensity is greatly depends on the atomic population. If the population is more, the excitation is more. If the excitation is more, the emission is also more. So in this way, atomic absorption can be measured. The intensity of the absorbed photons by the ground state atoms can be measured. Similarly, the intensity of the emitted photons by the excited atoms can also be measured by using a flame photometry. So this is how different atoms can be identified and quantified. So the spectral lines can be viewed through spectroscope. The spectroscope is a device which consists of a dispersing element whereby the lines can be viewed under a dark background. So the spectroscope is used to view you can view the spectral lines, those absorbed or emitted lines on a dark background. Whereas a spectrograph, so a photographic film is there. On that, the emitted or absorbed lines can be seen as dark lines. So on the colored background, the dark lines are observed in the case of spectrograph. Whereas the colored lines, that VIBGYOR lines, can be observed through spectroscope on the dark background. So this is how the atomic absorption and emission happen. Therefore, atomic absorption and atomic emission spectra gives you a line spectra. Unlike the molecular absorption emission spectra, the atomic absorption and atomic emission spectra gives us the lines. So the lines can be seen through spectroscope and lines can be drawn on a spectrograph. Thank you for watching and listening. Thank you very much.